Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In this section, we're going to talk about the potential control and the linear scanning voltammetry. In the previous section, we talked about the step potential change. That means potentials starting at a time equal to 0, step to another potential. But in this section, we are talking about the potential gradually, continuously change from one potential to the other potential. So this is called the linear scanning voltammetry, LSV. But I want to emphasize over here is that this scanning is at a low scanning rate. So that means whatever we measure is nearly kind of like a steady state condition. So the potential was scanning from one direction linearly to the other potential. We control the potential, and then we measure the current I. But the potential change is very slow. That means a d over dt less than 2 millivolt per second. In this very slow scanning rate. So we end with the voltage against the current. We end with this E versus I curve, or we can call the polarization curve. This one will give information is mean at the given potential what the current will be. This one is supposed to be you run a series of experiment measurement at one location, maybe for a few hours and at a steady state. But in actually experiment, usually we don't wait for so long. Usually we kind of continuously move the electrical potential, gradually move from one potential to the other, and record the current, and then we plot the potential against the current. So in this section, we'll talk about the linear scanning voltammetry at a very low scanning rate. So the result come out is more or less like a steady state condition. So this one, what in experiment we measure, we had a battery or fuel cell, and then we connected with an adjustable resistance, and then a voltmeter measure the voltage across the fuel cell, and then the ampermeter, the current measurement, is connected in series. Then we gradually adjust the resistance. Then from the infinity large resistance, gradually reduce. Then the voltage at infinity, there's been no current flow. You got the voltage very high. As long as when the resistance gradually reduce, then the voltage will be gradually reduced. However, the current will be increased. Eventually, we get this kind of polarization curve. In a modern time, though all this done is by mechanic automation, machine automation, and this one usually is we call it electronic load. They gradually adjust the equivalent resistance to make this measurement. This one, so we control the potential as a function of time, and the linear increase or linear decrease. Then we measure the current. The current actually recorded as a function of time. But when we plot the result, usually we plot the electric potential as a function of current in this way. And the potential is a linear function of time. So the phi I is the initial electric potential scanning from initial over here, and then at a scanning rate mu over here as a function of time. The scanning rate is usually the less than 2 millivolts per second. So all the data we measure is assumed to be at the equilibrium. So when we measure, we end up with the cell voltage against current time. So we can consider like a battery or the fuel cell. The cathode and the anode is separated by a membrane or separator. inside the membrane or separate the membrane acting like an electrolyte conduct the ionic conduction. It might be also the electrolyte, maybe like electrolyte separated by the electrolyte. When at the high voltage, the current at equal to 0, there's nothing. You just connect a voltmeter, connect the cathode anode, you measure the voltage. There's no current flow through the entire system. So this is schematic. If you put a probe, you measure the potential, then in the cathode, and then in the electrolyte or the membrane or the separator, you may say, and then the anode. That we assume this in the cathode anode electrolyte is quite conductive, so the potential is uniform across the entire medium. But at the interface, there's a potential drop over here, or the potential difference, and that's because the material is different. So naturally, the electric potential will be different around here at the interface. When we start that's we call and then the potential at this condition we call the open cell voltage, OCV here. The cathode, the potential minus the anode potential, the potential difference we call the cell voltage, and at the condition at the current equal to 0, so we call that it's open cell voltage. When we start let the current flow through, maybe you connect it with a fixed resistance, the current start flows through, and then the cell voltage will be gradually reduced. So the potential distribution or potential profile will be look like that. There will be gradual decrease, and then we further going down the potential, the voltage, or the increase of current, then the potential profile will be something looks like this. Inside here, over here is uniform, but inside the membrane or electrolyte, because of limited ionic conductivity, so this maybe had a potential variation inside the electrolyte. Usually it might depends on how conductive the electrolyte might be. So when we gradually reduce the electrode resistance in the external current circuit, or the increase the current, then the potential on the anode or the cathode will be changed. The change from the equilibrium potential we call the eta A at the anode. The N we call the anode over potential, and on the cathode also had the eta C, the cathode over potential. The difference between the cathode and the anode potential we call the cell voltage, and this cell voltage E cell is the cell voltage we measure here. So over here we can say the cell open circle voltage is the cathode difference between the cathode potential and anode potential at the equilibrium potential or at the I current equal to 0 condition. And then cell voltage is the cathode potential minus anode potential at the current not equal to 0. And this over potential of the cathode over potential equal to the cathode equivalent potential minus the cathode potential, or the reverse, the cathode potential minus cathode potential at the equilibrium. The same also for the anode over potential. So for the fuel cell or the battery at the discharge, usually you get a higher current, the cell voltage will be decreased. But for other process like electrolysis, electroplating, electroforming, electrochemical machining, or battery charge, the cell voltage will be increased as the current increase. That's because in this situation, for fuel cell battery discharge, they have the chemical energy, and then goes through the electrochemical reaction, release the electric energy. So the electric energy released, so you got is a spontaneous reaction. So the energy will be released from the chemical, and the release become electric energy. So you got a higher current, the cell voltage will decrease. But for the other situation is we input electricity into the electrochemical system like this, like electricity, electroplating, and so on. So the energy was supplied from outside the system, supplied through the electrochemical reaction at the electrode, and then making something change, and like the energy was transferred from electric energy into the chemical energy. So the cell voltage will be increased as the current increase. And for in this condition, the energy was released from the battery or fuel cell to the outer external environment, become the electric energy. So the cell voltage will be decreased as the current increase. The cell voltage doesn't matter which situation, the definition always similar.